to go a little faster this time, we're going to just go through what I put in the handout, because it, to some degree, it's a bit of, there's some review and then introduce a new thing. I'm going to get last Thursday, last Tuesday, and today's lectures, plus a supplement to last Thursday's, all on Canvas.
So for the solving the three-phase problem, under what title you put that in?
It will be Module 3, Lecture, I think it was Lecture 6, and I'm going to say Lecture 6-2. So there's going to be a Lecture 6-1. That's the one that we did Thursday, and then I'm going to add, if I'd had another half hour, I could have finished that. That'll be Lecture 6-2. And so that's what it is. Then you're going to see Module 4, Lecture 1, and Module 4, Lecture 2, all on Canvas. We're on Module 4, Lecture 2 now. So, yep. Okay, good. Okay, well, I want to drill down a little bit for a few minutes on what we're talking about in linear versus nonlinear systems. And recall that we derived this expression here. That's for energy. And if we have a system that is linear, then we can plug an expression for lambda, which is L times I, and the L has a position dependency. And in order we're really ending up trying to get to force and torque. Today we're going to talk about torque. I'm trying to get almost all of chapter 3 wrapped up except multi-winding. Maybe if I could get that far. So I'm going to talk kind of quickly here. But we derived the force last time from the energy, and force requires movement. That's why we have this position dependency of the inductance. So once we plug that in, you get this somewhat familiar expression of 1/2 Li squared, where the L has X dependency. Now, if the system is linear, I pointed this out last time, 2 key points. The first one is that the current can't have any X variation for it to be linear. If it does, it's nonlinear. And also L cannot have any I variation, otherwise it's nonlinear. In a sense, what I'm saying is that if you had a BH curve, the L would have to be in the unsaturated or linear portion of the curve. And the last time we also pointed out that we have this, instead of talking about BH curves, we can also talk about things in terms of a lambda I curve. To do that, we have to recognize that the lambda is proportional to B. If you question that, go back and look at Faraday's law. And the current is proportional to H. And if that's a question for you, go back and review Ampere's law. Okay, so we've been talking about this the whole time. So given that point, I'm saying that I could, instead of writing a BH curve, I could write a lambda I curve. And this green line that I've shown right here is looks a lot like a BH curve, right? It's essentially what it is. Now, if that's the case, what I can do is I consider areas bounded by a particular lambda and I combination. So I'm saying, for example, if I considered the lambda 1 and I1, lambda 1 and I1 here, then there's a curve. I've said that there's this little rectangle right here, okay, that's bounded by that. It's kind of like the area under that curve. And I could also consider a different point right here, say lambda 2 and I2. If I did that, I got another thing. So essentially what you're seeing is that I'm drawing a box around, in the case of the lambda 2, lambda and I2, a larger part of the curve. Now what you can think of is that the BH curve now divides up this box into two portions. So on the left-hand side portion, I'm going to kind of try to emphasize this. If I filled that in, that is the energy. That's really another way of looking at what we have just derived. If I look at the bottom underneath the curve, I come up with another thing which is called co-energy. And right here. So this is called co-energy. And we're going to derive co-energy. Co-energy is a much more useful quantity to work with than energy. Energy is extremely difficult to work with because of this linearity consideration. And I'm going to show you that. So what we really have then is the area above the curve, this area here, this blue area here, above that lambda I curve represents the energy, or what we derived was the WFLD. The area below that curve represents what we are now going to call co-energy, and it is a WFLD prime. We can think of then the total energy plus co-energy being this area under the lambda I, basically lambda I area. If you think of lambda as an X and I as a Y dimension, it's kind of like the area of that, right? It would be the product. That would be the sum of these two things. They sum up together to make that up, basically to make up these little rectangles that I showed here. And so interestingly now, if I designated two areas on this curve, the area 1, lambda 1, I1 area, is the linear part of the curve. In the linear part of the curve, we have the energy and the co-energy are equal to each other. And recall that we were able to go up to the, we'll show you again, but we were able to take this complicated expression that we had right here, and well, actually I did, we were able to simplify it. We did show you that, right? We're able to make it look like this if it's linear. So essentially that energy becomes this term in a simpler form in that region. If we go above, though, notice we have this saturation characteristic, and it's one example of a nonlinearity. And in that case, they are not equal to each other. These two areas cannot be equal. And so what I'm going to do now, is I'm going to consider go back to this expression right here, and let's rearrange it. So I can rearrange it and I can come up with this expression for co-energy. Now we recall that okay, so now what I'm going to do is I'm going to take the derivative of both sides, okay? So now I have a differential equation. That's what I'm after. If I want to find out an expression for co-energy, I need to take derivatives and find a differential equation and then integrate. So if I expand out using the chain rule for derivatives, I end up with this expression right here for coenergy. And I have now, this is the energy here, plus these additional terms. And recall that this is the differential, that's a differential equation for energy. So I'm going to take this expression right here, and I'm going to plug it into that. And I do that substitution, what happens is there's some things that cancel out. So I've basically taken this right and plugged it into there. As a result, these terms, the I d lambda terms, cancel. And I end up instead with a lambda di term. So the state variables for this, remember, and you may not all know what a state variable is, right? But a state variable is something that you have to solve an integral for to get, and and so you can identify, if you look at any differential equation and you look at the terms that are derivative terms, and that's your state variables. So your state variables are lambda and x here, flux and position. Here, the state variables now become current and position. So this gives us an indication that, well, then if we can use the current, I think we're going to end up with a simpler scenario that we can work with. Now to get that, we have to do what we did last time. If everybody followed, I'm going to go back quickly and show again. We went through this approach of trying to, in general, solve a differential equation having two axes and following a path that we can define. So we have these two paths, the path A, path B, that would get us through integration to this. In this case, now it's the coenergy. And along path A, we would be doing this. So here's path A. We would be integrating from 0 to x naught. Now in that path, I went a little quickly last time. The change in current, and last time I had the change in flux, is 0. So this term here is not in there anymore. And then the other thing is, I said that because you don't have any flux, you don't have a field, and therefore you can't have any torque. And that's going to be clear when we look at Lorentz force law in a little bit. So if you don't have a field, you can't have a force. And so this whole term then becomes 0. Everything here essentially is 0. So then you go back to the next one. Well, you've got the dx term, but there's no change in path B. So this is path B right here, and there's no change in x for path B. So this whole term is 0, and now you're just left with this. And so now what you have is the integral from 0 to I naught, which is just some arbitrary current position of the flux, and the flux is a function of current and position. We also recall that the flux linkage is the inductance times the current, so we can plug that into this expression and we end up with this. Now we get directly what we wanted, right? 1/2 Li squared. That's coenergy. This is general. This is the point I want to make very clear, that you will be able to use this term regardless of linearity. It works if the system's nonlinear or linear. Basically, one way to think of it is, if you were doing integration, and integration is, the area under a curve, would you rather work under the curve or above the curve? It's a heck of a lot easier to integrate by finding an area under the curve, I would think. Okay, so we've got co-energy now. Now let's go back and look at force. And I actually did something last time. I didn't finish the derivation completely, and I kind of made a jump, and I'm going to go back to. But before that, I'm going to find force. So we're going to say, let's find the force using co-energy. And to do that, we are going to go back and look at the differential equation, or the derivative of the co-energy. And we have two expressions. We have this is the expression we were working with right here, okay? But we can also come up with a new expression right here, which we simply apply chain rule to the co-energy. And we know that the co-energy is going to have variations with x and variations with y. So the partial derivative of the co-energy with respect to position can be evaluated, but the very important point is it must be at a specific value of current. So this becomes a constant, a coefficient. And then we can do the same if we want the partial derivative of the co-energy with respect to current at a specific x. We did this last time, but it was flux, not current. So it's very similar. So if I take this, we're going to basically take this expression right here. We recognize that we've got that force expression is like a coefficient times dx. And we have a coefficient times dx here. So you're really looking at these two expressions in a different way, where the derivative gives you, the chain rule gives you two coefficients times the two derivatives of state variables. Or we look at the differential equation that we came up with by considering, well, if we go back to the last lecture, I'm just going to jump there just for a second to remind you. We looked at this, remember where we started this whole process off? We were just looking at this general magnetic system, and we were inputting force and getting a current and a flux out if it was a generator, or if it was a motor or actuator, we're putting current and flux in, and we're getting a force and a position out. And so from this here, we were, remember, we came up with saying, okay, the force is equal to the energy input minus an increase in energy. That was the WFLD minus losses. We ignored the losses, right? And then we decided to take the derivative of both sides, and that's how we ended up with this expression. We took this expression, we plugged lambda back into the E, the d lambda dt now. That's voltage, right? We got this expression right here. And then we had, well, actually we got to this expression, and then we got to this expression right here. And then the DTs, we just said, okay, let's just get rid of them. Let's act like we're real mathematicians and use a formula that nobody understands. And then we have this thing here, right? A D, just a derivative, and it looks like this. Okay, that's how we got to it. That's one way. The other way is to simply do a chain rule which is what, so this says, okay, I've got my two state variable derivative terms, but these are coefficients, I and force. And then in the other situation, we said, okay, I have two coefficients. They're going to be lambda and force for the co-energy. And then I can make this equivalency of to the chain rule approach to the derivative, and I get that. So I'm just going, went back and ad nauseum trying to help you understand what we did here. What I really care about is the thing I circled in green, because I want to get an expression for force. I really don't care about this other term. So I end up with this expression. This is the general expression for force if I was given co-energy. And I'm going to review all of our equations that we derived in just a moment. This is again evaluated at a specific value of current. That must be remembered, okay? It's a typical mistake people make on tests sometimes, is not understanding that. Now, if we have the expression for L given to us, so if we know what L is, we can actually plug in our co-energy and come up with another expression for force. So if we go, this is where I made a leap last time. I'm going to go look at the energy again, but with the co-energy, it's extremely straightforward. I've got the derivative of 1/2 Li squared, and so evaluated at a specific current. So that means that there's no, it's just a constant. There's no, it does not impacted by the derivative. The only thing that's impacted is the inductance. And so if you evaluate this, you end up with this constant current squared over 2 times the derivative of the inductance. So is actually exactly, you can get the same expression from energy, but I missed a step explaining last time, so I'm going to go back and show you this. The force, as you recall, was, here was our expression for energy right here. And we are going to take the partial derivative of that with respect to x, but it's got a negative sign in front of it. There's no negative sign here, notice. But there's a negative sign here. So to make it easier, I'm going to say L of x is on the bottom. Let's put it on the top, so that's L of x to the -1. And so if you take the derivative of this, it's just going to cancel out that negative sign. And this is where we ended, and I was kind of dumb to end there because that's not the final expression. What we notice, what we have said here is that we are evaluating this at a specific flux level. Because of that, we can indeed use this expression, lambda naught, lambda at a specific current is the position-dependent L times I naught. So we can just go ahead and plug that into this final evaluated expression. So this goes in here, and it simplifies to this. So we actually get the same exact expression if we started with energy or co-energy. There's no difference. The subtle point here is this. If I did not have this term here, if I couldn't depend on the fact that I was evaluating it at a specific point, there was a nonlinearity in the system, which would have meant that this flux linkage would also have an X dependency. I would have had to make the substitution before I did the partial derivative, and I would get a completely different expression for force, and it would be the wrong expression. And I showed you this example from the textbook, which was see, the textbook goes through this very clearly. This is why I tell you this is a good textbook, because I didn't know any of this when I came back to school after working for 21 years. I never learned what coenergy was. Every time I read a paper about motor drives, it was written by an academic. They talked about coenergy, and I had no clue what they were talking about. But I designed motor drives and things like that from 24 years not knowing it. But it's extremely helpful to understand this. But so this is this really, let's see, I think it was example 3, 4 that we went through. Okay, so this is really from a physics perspective, Lorentz force law. This is the 4th law that we cover in this class. And this is a 3-dimensional, so just like every other law, we can start out with this 3-dimensional expression. It can be applied in any coordinate frame. And this is the general physics-based expression for Lorentz force law. It's the force, F, which everything is an SI unit. So the SI unit that we use for force is newtons. The electromagnetic force is equal to this expression here, where Q is a particle of charge in the presence of electric and magnetic fields. It has the units of coulombs. E is the electric field intensity. We've already introduced that before with Faraday's law. It's volts per meter. The V is a new thing here, this V. The V is the velocity of the charge relative to the magnetic field intensity H in this system. And it has the units of meters per second. We've already introduced flux density, that's the B. It's corresponding to the same, essentially, H that we were talking about above there. Basically, remember, B is equal to mu H. So if you have a B, you have an H, they're just different by the permeability. And then the A Tesla was the unit that we used before, right? And that was the same as Weber's per meter squared. Ends up being equal to Q times E plus Q times V cross B. So luckily, we're not, this one we're going to get rid of. We're going to say, let's leave this to the quantum physicists, okay? I only care about copper and iron, okay? So this is what we're going to focus on right here, because I want to see things that move and do stuff that I don't need, that I don't have to look at very high frequencies, with a spectrum analyzer. I can actually see some motion here. So we're going to talk about this guy right here. And we can rewrite this expression as force equal to let's see here for a second here. I want to make sure I don't make a mistake. We can write it in terms of a charge density. So we're going to introduce charge density. Okay, so it's this rho, charge density, and rho has the units of coulombs per um, cubic, let's see, is it cubic meter? Yeah, cubic meter. And so because we did that, we can write the force as um, well, I'm going to skip the detail here, right? Because I'm just going to give you the final answer here because I want to go fast and I don't want to talk about current density right now. So essentially, I think I can do that. I take it back. I can write the force as J cross B. So I'm really trying to get things in terms of a current and a field. And J is equal to this charge density times V. And this is one other thing. This is going to be the force per cubic meter. That was the thing I was getting myself screwed up about. So I'm going to put this little sub V here. It's per cubic meter. So I've essentially taken this expression here and divided it by meters cubed to get FV. And I get this term here. And then if I have that term, I can go back and I can multiply it out times the meters. And it's really kind of allowing me to use this rho term is why I did it, because then I can say this is the general expression used by, you might have seen it in your EE361 class for the current density, but it's this particle density times the velocity of the particles. But now let's get into real world stuff. If I multiply back out by meters cubed or volume, then I can get a new expression, which is I cross B. All the units will come out, and essentially what this is this is the Lorentz force expression that I have always used. And it is I F equal I L cross B. So here's the final thing. And now I can actually apply this to the structure that we're talking about. This is the B vector. This L is a position vector in one direction or along one line. If you pick the right coordinate system and line up your L on one axis, then it's going to simplify everything. And so essentially, if you use Cartesian as opposed to, we could use Cartesian or we could use cylindrical. Line up L on the z-axis. So essentially the L becomes LZ Z. I think this is the way it's usually expressed. And now let's go back to this picture here. We've lined everything as far as the field. So the green field winding produces the B, which is ending up being BY in the Y direction. The L here is the length that this winding is running down the rotor. And so it's actually inside what we would call a slot. There's a slot in this structure, and the length of that slot that is carrying the current, I erased it with this stupid button on my pen. Okay, it's going down the slot here. It's coming back the other side, so you've got a wire going in here, and you've got a wire coming out here. There's a current going in there. We could call that current IA, armature current, going down the length. And so this is the z-axis. So essentially we have L equals L, the length, times the z. So we only got a single dimension in each. They're in quadrature with each other, x, y, and z. That's what we want to get to, because then we can have a very simple expression. What we can do is we can then also come up with the right-hand rule here. So I've got my picture of my hand here, and I have a current. I'm going to actually use this expression here. I've got my current running down this length. This is along a z-axis. This is L. And the current in that, and I'm ignoring the dimensions of the wire. This is I. And so I'm taking I, and there's a B that's going in this direction right here. This is the LZ here, the I, and I'm going to do the cross product. It's a little bit difficult. I got to start at the middle of this is the middle of the rotor that's carrying this current, one side of the current, and I'm going to go the I, my hand is going down the current. This is where we get screwed up because I'm not in front of you. Going to go I cross my fingers. I'm going to turn my hand. Here's my hand. I'm going to turn it. Outward towards you. There's the palm of my hand. It's ridiculous. You can just see the comments on the evaluation here. Okay, IL cross the B. I'm going to end up with a force in this direction. in the direction of my thumb, bottom line. And that's what's going to happen. So essentially what's happening is each of these, this picture I drew right here gives me a force due to one side of the current winding and another force here on the other side of the winding. So the force is pushing out on the wire. Does that make sense?
Yep. Yep.
Okay. All right, but this isn't real helpful to me because really what I need is I need to deal with something called torque. So I'm going to just show you this picture. This is from the, I didn't have time to pull this in. If I going back to this picture here, this is what I just described, and I have a very cleaned up. I'll put the module 5 notes. They're already actually up on Canvas. This is the force, but now let's introduce torque. And this is the expression for torque right here. Torque is R, so now we have an R vector going radially out from the center of this whole thing. So that's essentially saying that I've got this thing right here I'm talking about, pointing out from the center to where this conductor is, and I'm going to do a cross product with the force dimension. And what I ended up in this case, I can tell you that this is right because I did this over and over, and I did it again when I was making these slides. But the force, now this stupid thing is stuck. Hold on. I end up at torque, and the torque is actually in the shaft direction. That's the point. Let's see if this will highlight. I don't know if it'll even highlight that. I have to draw a circle around it. Okay, so the torque is along the shaft, and it's just think about a screwdriver. Okay, torque is a screwdriver. You grab the handle of a screwdriver and you push and you twist, and that's torque. And the bigger the screwdriver, the more torque, right? The bigger the handle. So anyways, that's how you get torque. And if you work out this problem here where we said, okay, I'm assuming this angle here, trying to get my pen back, I'm calling that a torque angle. I've actually got two sides of the wire, so there's actually going to be a factor of 2 in this whole thing. And now I've got a new expression. I've actually have an expression for force, but right now, because I have a rotating machine, force is really not useful to me. What is useful to me is torque, because that's what's going to do the work. And this is the final expression right here for the torque. And it's a scalar expression. There's no vectors or anything because of the way I've chosen the coordinate system. And it's a function of sine times the torque angle. So if I have a constant field that's producing a flux density, I have a rotor, I have a round rotor that's fitting inside of a round space and the rotor is carrying a current I. Then if I take the product of I times the flux times the sine of the torque angle, and it ends up being negative, then what I end up having here is I've got a torque expression, a general expression for it, and it's the sum of these two torques from both sides of the winding, the way I'm expressing it. And in a sense, you can say, well, what is this 2? The way this is it kind of correlates to n. And we're going to get to some real general expressions here. But one question I have, I know we're like 4 minutes over, but what I want to do is I want to get torque is what's doing the work. I want to get the most out of my machine for the least amount that I'm putting into it, right? So what is it that I'm putting into this machine? It's a question. If you guys, to get out of here fast, can somebody answer? What am I putting into this machine?
Mechanical input via rotation.
No, let's say it's a motor. I'm trying to get mechanical out. So I have to put something in. Going back to the very first thing, right?
Current.
Current and what? The current here, what's the B represent? It's proportional to flux, right? Current and flux. So essentially, we also learned, right, that lambda is L times I. So there's another current. It's a different current. It's a field current. But I have 2 currents, or I have to buy magnets. Regardless, I have to put stuff in, and there's going to be losses and cost associated with the current and the flux. And for a given current that I put in, I want to get as much torque as I can out. So what is the angle that I would want to have to get max torque per, let's say, ampere, or max torque per dollars? What angle do I need? You guys should know that. What's the sign? What would give me the maximum torque?
45 degrees.
Not 45, no. 45 would give me 0.707.
Would be
What gives
90.
me 90, right. I get 90 degrees is the max torque per ampere. DC machines are designed to always give you 90 degrees. And basically, the torque angle, so the point is that del torque angle equal 90 degrees gives you this. If the del is less than 0, if it's negative, it's a motor, because we're going to define that a motor gets positive torque out. If I have to put torque in, I'm going to call it a negative torque. And so if del is greater than 0, it's a generator. So we've come full circle back to the magnetic structure, and now we're finding torque, really coming completely full circle back to this last point here, at the very beginning, right? We're really talking about this now. I put current and flux in, I'm going to get a torque out of my magnetic system. And I've shown you a magnetic system. The magnetic system I'm showing you here is this gray stuff right here. This gray stuff here is iron. That's like a stack, right? And you got it on the rotor too. And I've got copper and iron. And I'm coming back to this. And that's my magnetic system. And I can get a torque out and a rotational position that does the work. Or I can put the torque in. Now it's a generator, in which case torque is negative. So this has del greater than or equal to 0, or greater than 0. If it's 0, I'm not getting anything out. The torque angle. This has torque less than 0. The torque is proportional to the negative torque. Last point, and then I apologize. Torque is proportional to the negative of the sine of del. Del is torque angle. Okay, so we're almost done. I'm just going to give you some examples and we'll go into Map Module 5 next time. Okay? Any last questions?
Will you be posting your annotated notes up for this?
Yeah,
Okay, thank you.
I will definitely do that. I've already got these notes will be posted. Okay, well, you guys all have a good day.